Hello. Uh, I'm going to talk to you today about something called metamaterials. And the title is Beyond Materials, Metamaterials. Basically, these are artificially engineered materials which possess, unusual properties, and I'm going to go into them later in the talk. So it starts with Einstein's theory of general relativity. So basically that's a sort of loose mathematical framework where space and time is distorted by matter. So we've got an example of a gravitational lens there, where the galaxy is distorted by the black hole in the center. So lenses go back a long time, from sort of the start of civilization, where they first discovered lenses in 2000 BC. Black holes also result from a singularity. So this is all relevant because this is the mathematical framework behind transformation optics, which is an offshoot of metamaterials. So what is transformation optics? Basically, I've mentioned astronomy, and you have thermal cloaking. So one of the applications is cloaking. So you can have thermal cloaks, cloaking for sound waves, cloaking for matter, where you use the equations to cloak electrons going around a hidden insulating shell. So there's a picture of one there. So it's a nice program to use. Finite difference time domain. You use it in MATLAB to simulate electromagnetic waves. So I've got some equations on the right. So on the left is the ray, and on the right is the distorted ray. So I can just show a bit of code. Okay, maybe not. So this is a simulation of the cloak. You've got an electromagnetic pulse from the left. Cloaking takes place there in the cylindrical region. So I mean, in theory, you could cloak anything. I mean, you've got different methods. You can cloak tanks in the infrared. Some people have tried to use projectors on a screen that they're wearing to project the image behind them. So basically, invisible to human eye. So what gives these cloaks their interesting properties? Things called metamaterials. So these are electrical structures, combinations of capacitors and inductors. They're usually sort of split rings. And here, you've got an example there. So I mean, cloaking's invisible. I've mentioned some sort of applications and stuff already. So I mean, an innovation in the cloaking field, I suppose, which I've done my PhD on and stuff, is to cloak something underneath a carpet. Effectively, it's called like hiding something under a carpet. So this is possible using an all dielectric implementation. So instead of using anisotropic materials, you would use isotropic materials made of a single block of dielectric. So this technology is basically, I mean, it's got some interesting applications there, but basically it's going to revolutionize, satellite communications. So currently, you've got antenna dishes. They're sort of parabolic, and you can create sort of flat dishes. So you're saving space and cost and things. So I mean, I've showed the video. It's something fun to play around. I mean, you need MATLAB to run the codes. Another interesting feature is negative refraction. So conventionally in a lens, you would have refraction. And in negative index material, you would have negative refraction. So, that's what else? You have negative Cherenkov radiation, which is the radiation from nuclear reactors. It glows blue. So I wasn't able to show you the code, which is quite interesting. So I've mentioned it's got lots of applications. So you can design thermal cloaks where you're cloaking something from heat, basically. Sort of, you can have mechanical cloaks, so you have negative compressibility. So it's basically sort of covering lots of aspects, really. So I've mentioned satellite communications. You can transform flat dishes to parabolic dishes to flat dishes. You can also do that with lenses. So you can transform curved lenses to flat lenses, saving like space and cost for optical engineers. So you can do some fun sort of Fourier optics and calculate the reduction in the wavefront in sort of transformation optics lenses. And I think that's it. Are there any questions? Well, it mostly works on microwaves, so a lot of experiments are done sort of at 8 gigs. When you're getting sort of optical frequencies, it's more difficult, and people tend to use silver.
So I was thinking, if you're going to do lenses and that sort of thing, surely they're technically quite difficult to make a lens that will have a negative like refraction. The actual technical requirements to make the lens must be significantly more difficult than other.
Yes. I mean, that's why the sort of methodology has moved away from metamaterials, which have negative refraction. to transformation optics, where you're kind of having an anisotropic material. So you could do a similar lens, but it would be anisotropic. You can use silver. I mean, it's quite lossy. Like I say, I mean, it's easier to replace them with transformation optics media, which is kind of like anisotropic. And you could do that with something like, there's a foam called barium titanate foam. So you sort of, it's a foam, and then you have a distribution of particles in the foam, which gives it the variation of permittivity. Well, it's generally blocks. I mean, you discretize the map, and so you've got blocks of single permittivity materials. Yeah, I mean, as long as it's small in the wavelength.
Do we have any other questions?
So basically, it's made from, it's a resonant phenomenon. So basically, you've got the permittivity and permeability, which combined gives you the negative refraction. So by using a split ring resonator, you, at the resonance frequency, you get a narrowband region where you've got negative permittivity. So yeah, so I mean, that's.
Is there another question, or shall we just wrap up at this point? Very well.